Today we will study about the hash functions and see how they secure the bit flip attacks on the stream cipher. So let's say there is Alice, there's Bob, and there's Oscar. Now Alice wants to send a message with a fingerprint to the Bob. Now, this fingerprint is the hash function evaluated on this message. So now Alice sends the message and sends the fingerprint to the Bob. This is the working of the hash function. Now we see how this hash function makes the message secure against the bit flip attack. So the Alice generates message in the fingerprint, and now suppose Oscar just traps the message. Now Oscar does some changes and then send it to Bob. Now Alice has sent its fingerprint to the Bob already. Now Bob computes fingerprint of the received message, the message which the Oscar just sent it. Now this is the fingerprint of the received message. Now Bob equates it with the fingerprint that he has received from Alice. Now if both of these fingerprints are same, then Bob will accept the message, otherwise reject the message. Now we look at a practical example of hash function. So we create a new file and we name it hash.py. Now to use hash function, we import from crypto.hash and we import a hash function known as SHA-256. Now SHA-256 will give us a fingerprint of size 256 bits. Now we create a data. So data, we write it as a message: we will not come to office tomorrow. And now we calculate its hash. So hash function equal to SHA-256.new data. So the hash function works something different than the cipher. It doesn't need any initialization. And I'm talking about the unkeyed hash function like this, SHA-256. So it just needs the data to compute the fingerprint. Now we print the fingerprint produced by SHA-256 of this data. Print fingerprint is, and we write print hash function dot digest. So this is the digest of this hash function, and let us see if this works. Okay, yeah, so it has given us the fingerprint in this form. Now we check if it is really 256 bits or not. So we write print size in bytes of fingerprint is, and we print here hash function dot digest size. We click on run and we see that the size of the fingerprints is 32. Now 32 is in bytes. If we want it in bits, we print hash function dot digest size and we multiply it into 8. So we give one more print statement: size in bits is. And now let's see what is the answer. So we see that the size is 256 bits. This is the fingerprint of our data. Now we will see if we change even a single bit of this data, the whole of the fingerprint changes. Now we can use this method of flipping one bit, which we have already done. So I just copy this function and I paste it here. Now we change the data. We make it modified data equal to flip one bit of the earlier data. Now hash function 2 equal to SHA-256 dot new, and we give here the modified data. Now we print the value of the digest. And let's see what is the difference. Okay, so there is some error in here. Positional one agreement in the module flip one bit of the data. Okay, so we haven't mentioned that which bit we have to flip, so we put here wait, there is some error, data and int. Okay, so we need data and we give here the position, say at the 6th position. Now we run this file. Now we can see this is the fingerprint of the first data and this is the fingerprint of the modified data. You can see these two are entirely distinct. This shows that even if you change one of the bit, the fingerprint is going to be changed entirely. This makes the plain text safe from the bit flip attacks.